You know, physics is amazing. It gives us these incredible rules for how the universe works, but it often stops short of telling us why. Why is energy always conserved? Why does everything in nature seem to take the easiest possible path? Well, in this explainer, we're going to dive into a fascinating new idea that might just provide a real physical mechanism behind some of the deepest laws of reality.
So let's start with a big one, the conservation of energy. The official answer from physics is that it's due to a time symmetry. But let's be honest, that's a rule, right? It's not a physical reason. What's actually, physically, stopping energy from just winking into existence or vanishing without a trace?
And then there's this other weird thing. Everything, and I mean everything, from a beam of light to a planet in orbit, seems to follow the path of least action. It's like it knows the most efficient route from A to B before it even starts. The principle works perfectly, but the reason why feels, well, it feels kind of like magic.
And finally, we've got the most famous mystery from the quantum world. We're all told that an electron can instantly jump from one energy level to another without ever traveling through the space in between. I mean, how is that even possible? What's physically going on in that instant? Standard physics gives us the rules for it, but not a picture we can really wrap our heads around.
Okay, so we have these three huge puzzles. A theory called dynamic vacuum field theory puts forward one single, pretty radical answer to all of them. And it all comes down to the idea that we've been thinking about empty space completely wrong. This is a massive shift in perspective. The standard view, the one on the left, basically treats the vacuum of space as a passive, empty stage where the drama of physics unfolds. But this new theory says, no, 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 the vacuum is the drama. It's a real physical medium with its own distinct properties. So what are these properties? Well, the first one is called amplitude. The easiest way to think about it is like density or substance. It's what gives space the ability to store energy and to have inertia. In this picture, things like mass and energy are just localized clumps of the vacuum's amplitude. And the second crucial property is phase. Now, if amplitude is the vacuum's substance, then phase is its internal clock, its rhythm. It's what allows the vacuum to oscillate, for waves to move through it, and for time itself to tick forward. It's basically the engine that drives all change in the universe. All right, so let's keep those two ideas in mind, a dense, rhythmic vacuum. Now we can go back to our original questions, and you'll start to see how these abstract, magical-seeming rules can transform into physical, mechanical causes. This quote just nails it. The universe isn't some super intelligent calculator figuring out the most efficient path. The answer is much simpler and much more physical. It's because the vacuum is stiff. So here's how it works. Action is no longer just a mathematical idea. It's the actual physical cost of bending or stretching the vacuum. And just like a stretched-out rubber sheet, the vacuum resists being deformed more than it has to be. So a particle, or a wave, naturally takes the path that creates the least amount of total strain. The path of least action is literally the path of least resistance. So what about energy conservation? The explanation becomes beautifully, elegantly simple. Energy is conserved for one reason. The vacuum can't forget the shape it's in. It's not a magic rule, it's just a fundamental property of the medium itself. The logic is actually pretty straightforward. If energy is just the shape of the vacuum, a dent, a ripple, a deformation, and the vacuum itself is the bedrock of reality that you can't create or destroy, then it follows that its total amount of deformation has to stay constant. You can change the shape, say from mass into radiation, but the total amount of strain in the vacuum stays exactly the same. But this brings up another deep question. The basic laws of physics work perfectly fine forwards or backwards in time. So why do we only experience time flowing in one direction? Why does a dropped glass shatter, but we never see the shards fly back together to make a whole glass? The answer seems to come down to statistics. Imagine a drop of ink in a glass of water. It starts out as this nice, orderly little blob, but it will always spread out and become disordered. It never spontaneously gathers itself back into a drop. This theory suggests the vacuum has a huge hidden microstructure. Organized energy naturally leaks into this scrambled, messy state. And that one-way flow from order to disorder is what we experience as the arrow of time. Okay, so this idea of a physical vacuum seems to provide some really satisfying explanations for the big rules of the universe. But what about the famously bizarre quantum world? Let's see if the same core idea can help us make sense of it.
The number one rule of quantum mechanics is that things come in discrete packets, or quanta. An electron can be in energy level 1 or energy level 2, but never at level 1.5. Why? What forces this discreteness? This is where the guitar string analogy is just perfect. When you pluck a guitar string, it can't vibrate at just any random frequency. Only very specific frequencies, the ones that form stable, standing waves, can actually last. We call those notes. Any other vibration just cancels itself out and dies away. Well, in this view, quantum states are simply the stable notes that the vacuum is allowed to play.
And this all comes down to the vacuum's phase. Remember, we said phase is like an angle. So for a repeating pattern, like an electron in an orbit, its wave has to go all the way around and meet back up with itself perfectly, in a whole number of cycles. If it doesn't close on itself, it's unstable and it just fizzles out. This simple, geometric requirement is the physical reason for all quantization in the universe.
So this brings us all the way back to that quantum leap. What is really going on? This statement here totally turns the old picture on its head. There is no travel. It's not a journey. It's a reorganization. So an electron isn't a tiny little ball zipping around. It's a stable wave pattern in the vacuum. When it absorbs a photon of energy, that old pattern becomes unstable. The entire field then, globally and almost instantly, snaps into the next available stable shape, the next higher note. It doesn't travel from A to B. The entire system just reconfigures from pattern A to pattern B.
So let's just pull all of this together for a second. We have seen how one single change in our thinking, treating the vacuum not as emptiness but as a real, physical medium, might offer a mechanical explanation for some of physics' most fundamental and most mysterious principles.
This table really says it all. Where standard physics gives us abstract rules and principles, this theory proposes actual physical mechanisms. Least action isn't a principle, it's because the vacuum is stiff. Conservation isn't about symmetry, it's because the vacuum itself is permanent. Quantization isn't just a postulate, it's because wave patterns have to close on themselves. And the quantum leap isn't an unexplained jump, it's a pattern changing its shape. It's a profound shift from saying that's just the rule to understanding this is how the machine actually works. And that right there is the ultimate promise of a theory like this one, unification. The idea that the majestic dance of planets and the weird little jumps of electrons aren't governed by two separate sets of strange rules, but are both just behaviors of a single, underlying physical substance.
But an idea this powerful and this profound, of course, leaves us with one final, even deeper question. If all of reality, matter, energy, space, and time is just the behavior of the vacuum, then what is the vacuum itself? And that's a question that takes us right to the very edge of physics and leaves us all wondering,